All right, guys, so taking a look a little bit further at systems of equations and specifically matrices. So we started talking about this last class, but let's look at a couple different ways that we can actually represent a system of equations, and this is a pretty basic system of equations. So the first one is obviously to write the equations. The second way that we can do this is with the coefficient matrix, and we multiply that by x, y, the matrix x, y, we call the solutions matrix, and then set that equal to the constant matrix. So that's another way that we can do this, and this is also how we use matrix algebra in order to solve this. We would find the inverse of this, multiply the inverse by both sides, and then that leaves x, y by itself and gives you your solution when you multiply that out. Another way that we can write this, though, is using what we call augmented matrices. So augmented matrices essentially is just a simplified version of what you see here. So we're still gonna use the coefficient matrix 2, -3, 1, 3, but we're gonna augment that or kind of tack on to that coefficient matrix the constant matrix that's related to these equations. And so this is what an augmented matrix would look like. The other way that we can use augmented matrices is to augment that coefficient matrix with the identity. And we'll see why we would want to do that here in a second. But if I augment this coefficient matrix with the identity, we're essentially just kind of tacking on the identity matrix to the coefficient matrix right here, and we would rewrite it like this. So these are two different ways that we can augment a matrix with something else. Here we augmented the coefficient matrix with the solution matrix, 5, 1, when we were given a set of equations. And here we augmented this matrix as 2 by 2, which may be a coefficient matrix, it may be something else. In this case, it is a coefficient matrix, but we augmented that with the identity matrix. And again, we'll check out why we would want to do that here in a second. All right, so now we want to check out what we can do with these augmented matrices. And what we can do is perform row operations on these augmented matrices. Generally, there are three different types of row operations. Number one, we can multiply a row by a scalar. And if you think about what's going on here, we're really just taking an equation like this, and we can just multiply that thing by -2. And as long as we do it to every term, as long as we distribute that to every term, no harm done. We still have an equivalent expression. So that's what allows us to multiply this row by a scalar. What that looks like, and again, we'll go through this specifically what that looks like for a particular problem, but if I want to multiply a particular row by 2, then I would say 2 times that particular row, row 2, R sub 2 stands for row 2, and we're going to set that equal to row 2, meaning I'm rewriting row 2 as now 2 times row 2. And again, we'll get to exactly what this means and how we lay this out in a second. The second thing that we can do is we can swap rows. We can swap rows. If we go back to our original here, instead of multiplying by a scalar, we can actually take these two rows and I can say, hey, I want row 1 and row 2 to switch. I want row 1 and row 2 to switch. And if you think about that, it doesn't matter what order we present these equations in. They're two separate equations. And it's the same thing for matrices. When we have our matrix representation, I can take two rows, one row here and one row here, and just flip-flop the order. And again, no harm done. I haven't really changed anything. I've just kind of changed the order. Okay, so what that looks like is row 2 now becomes row 1. So I've swapped rows. The third thing, and this is really the most useful, is I can multiply or combine, I should say, or replace one row with a linear combination of another. And generally, this is the most useful. And if you think about what's going on here, when we say linear combination, we're really saying, like, if I want to multiply this by, for instance, -1, and I want to multiply this one by +2, well, the reason that we do that is so that we can eliminate a particular variable. Okay, so the way that we do that in row operations is we represent that as, that would be negative row 1 plus row 2, plus 2 row 2, sorry, plus 2 row 2. And we can replace one of these rows with it. So generally we're going to replace one of the bottom rows, although that's not always the case. So this is going to become my new row 2. So really all this is kind of like an elimination method for matrices. Okay, so those are my three operations. I can multiply a row by a scalar, and this is the notation that we use. I can swap rows, and this is the notation that we use. And I can replace a row with a linear combination of another, and this is the notation that we use for that. All right, so the best way to do this is to kind of just jump into it. So first thing I want to do is I want to show you one of the uses, and one of the uses of row operations is to find the inverse of a particular matrix. And so you can see this is the given coefficient matrix. And so what we do is essentially we take the original matrix, the 2, -3, 1, 3, and I'm going to augment that with the inverse matrix. Okay? All right, so when I'm doing this, the goal here is on the left side to get the identity matrix, 1, 0, 0, 1. And on the right side, what will end up is through these row operations, if I can get the identity matrix on the left side, then what will end up is the inverse on the right side. And that will be augmented with it through these row operations. All right, guys, so let's go ahead and jump right in. So remember, the ultimate goal is to get this out of the left side, okay, through row operations. So the first thing that I'm going to do is I'm going to take row 2, and I'm going to add it to row 1. And it doesn't really matter the order that you write it in. What matters is what row is being replaced. So if I add these two, I'm going to replace row 1 with it. And the reason that I'm doing that is because when I add these two, I get a 0. Now think back to where we want to end up. We want a 0 in the top row and not the bottom row. So that's why I'm replacing row 1. So when I do that, I end up with something like this. Now, I can't just add these two. I have to add everything, just like in elimination. So if I add row 1 and row 2, I get 2 plus 1 replaces my row 1 entry. My bottom row stays exactly the same. So it might be a good habit to get into to just rewrite your bottom row if that's not the one that you're replacing. Everything else stays the same. Okay? So add my 2 rows. That replaces the top. I get a 3 in the top row. My second entry here ends up being a 0, which is nice. That's what I want. And then over here, I've got row 1 plus row 2 is my new entry. Row 1 plus row 2 is my new entry. All right, so this is after one operation. As a general rule, guys, and this is important, as a general rule, you can only do one operation at a time. One operation at a time. Okay? So the next operation that I want to do, I want to try to chase this. I've got a 0 up in this top corner here. I want to try to chase a 0 down here. So the next operation that I might do is a linear combination of these two. So I would take row 1 and I would subtract 3 times row 2. And where do I want the 0? If I take row 1 and subtract 3 times row 2, I want a 0 right here. So I'm going to replace row 2 with that entry. Again, row 1 didn't change, so I can go ahead and copy that one down. And go ahead and perform this operation for the second one. So 3 minus 3 times this entry is going to give me my 0, which is nice. 0 minus 3 times row 2 is going to give me a -9 in this entry. Row 1 minus 3 times 0 is just 1. And then 1 minus 3 is going to give me a -2. Okay, so I've got a relatively simplified. You can see I'm getting pretty close. I've got zeros where I need them. I've just got to do a couple quick things here in order to change it. The first one is if I multiply this top row by 1/3, then I'll get my 1 in that first entry. So that's exactly what I'm going to do. And this is the scalar multiplication. So 1/3 row 1 is going to replace row 1. Again, row 2 doesn't change. Let me go ahead and copy that down. Make sure I don't change anything there. And then 1/3 row 1 here is going to give me my 1. 1/3 of 0 is 0. 1/3 of that is 1/3. And 1/3 of this is 1/3. And the last thing that I need to do is I need to get a 1 right here. And in order to do that, again, it's going to be scalar multiplication. So I'm just going to take -1/9, multiply that row 2 by -1/9, and that'll give me a 1 right there. And that's exactly what I need because that'll give me the identity. So let's go ahead and go through that. My top row stays the same. And that's 0, 1. This entry times 1/3 is 1/3. I'm sorry, -1/9 is what I need to multiply it by. So this entry times -1/9 is -1/9. This entry times -1/9 is +2/9. And so now you can see what I've got over here on this left side is the identity. That's what I need. And over here, this is my inverse. And you guys can check that, confirm that with your calculators. But my inverse, it says find the inverse of the given matrix. So my inverse matrix is going to be 1/3, 1/3, -1/9, comma 2/9. There's my inverse. And so that's one way that we can use row operations. The other way, or another way that we can use row operations, is to solve a system. So if I write this as an augmented matrix, augment it with the solutions, the solution matrix. Again, the goal is to obtain the identity matrix on the left, and ultimately we'll be left with our solutions on the right, because if you remember, this is the x entry, so this tells me that x is equal to whatever we end up with here, and y is equal to whatever we end up with here. And so let's go through that process. So the first thing that I want to do, probably smart, is to, because I want a 0 for this entry right here, I'm going to add the first and second row, so row 1 plus row 2, and I'm going to replace row 1 with that linear combination of the two. So again, my row 2 stays the same. Make sure we don't change anything. We can recopy that before we do any calculating. Row 1 plus row 2 gives me a 3 for right here. Row 1 plus row 2 gives me a 0 here, which is nice. Row 1 plus row 2 gives me a 6 for that entry. A couple different ways that you can go about this right now. You can multiply this by the scalar, or you can do a linear combination and get your 0 down here. I'm going to go ahead and multiply row 1 by that scalar that I need. That scalar happens to be 1/3. So 1/3 row 1 is going to equal row 1. So I'm just replacing row 1 by a scaled version of itself. That'll give me my 1 and my 0, and then a 2 for that entry. My bottom row stays the same. Next operation is I've got to get a 0 right here. So I can just add row 1 and row 2 now because I've scaled it down. So row 1 plus row 2, and that's going to replace my second row now. Again, the top row stays the same. And the bottom row is going to be row 1. I'm sorry, that should be minus row 2. Let's fix that. Minus row 2. Because we want a 0. So row 1 minus row 2 is going to give me my 0. Row 1 minus row 2 is going to give me a -3. Row 1 minus row 2 is going to give me a 1. So there's that. And then the last thing is to scale this by negative 1/3 so that I can get a 1 in that entry. Top row stays the same. I'm going to take negative 1/3 row 2, and that's going to replace row 2. So top row stays the same. Negative 1/3 times 0 is a 0. Negative 1/3 times negative 3 is a positive 1. And then negative 1/3 times 1 is negative 1/3. So you can see again, I've got this identity matrix on the left side of the augmentation, and then on the right side of the augmentation, I've got my solution set. So what can I conclude from this? Well, I can conclude that x, y is equal to 2, negative 1/3. Or in other words, x is 2, y is negative 1/3.